This is IAT 806 Lecture 9, where we're talking about linked lists and binary trees. So the reason why we're talking about this is that in order to make computers able to process data quickly, one of the things that can be vitally important is to store data in a manner that's consistent with enabling efficient processing of data. So far in the course, we've talked about small collections of data, the triangles and rectangles for a rocket, the polygon or 2 or 10 for the asteroids you may draw, the things that went into composing your cool clock, stuff like that. And so there is a lot of processing going on behind the scenes for drawing polygons and, line segments and stuff like that. But one of the things that goes on there is that behind the scenes, the graphics card is doing a lot of the heavy lifting to enable that. But you can't quite say that there's a large amount of data being processed by your program directly. It's more or less being specified for the graphics subsystem to handle. And, we're not going to get into graphics processing algorithms, but one of the things I did want to talk about in the course is what are the standard techniques of managing large collections of data. And the reason why this is useful is, first, so that you can recognize and understand the trade-offs that come into play to enable those kinds of algorithms to work, and also for you to access those and understand what the names mean and what they do and what their behavior is like. So we'll talk about that a little later on in a later lecture, where you can have access to the stuff I'm talking about here that has been developed and provided for you within the Java development kit. So one of the primary ways of managing larger collections of data, say hundreds or thousands or millions of data items, all of the same kind, is that you have what is called a data structure that manages the organization of data and enables certain types of things to happen reasonably quickly, because the algorithms to do that processing have been researched and efficient methods have been found. So in data structures, with a collection of data, you often want to do many different things. And some programs need to do some of this stuff a lot and other things not so much. But first, let me iterate, so to speak, go through the list of these things here so that we can talk about the stuff that a data collection needs to be able to support when you're using it within your program. So the first thing is that your program needs to have a structure that stores and organizes data. That's the basic requirement. You need to store the data that you're processing. But organizing it might be useful given the kinds of tasks that you wish to do with that data later on. Another thing that's very, very common is to iterate over the data and do something per item. And in the graphics subsystem, say in the draw function, the void draw function that you define in processing code, that fundamentally is iterate through all the stuff I'm going to draw type of activity. And so we're doing iteration all the time, either implicitly or explicitly inside the draw function. And so that's kind of like the first thing that you want to do. You've got a collection of data, you need to do something with it. When you're doing drawing, you're drawing it every 30 times per second. So that iteration is very important. Another thing that we want to do, and we've talked about this already, is to add new data. So think of the Rocket and Asteroids program, adding new asteroids. When your rocket shoots a missile at an asteroid and it breaks into two, you need to add 2 new smaller asteroids, if indeed it was a large asteroid that you hit. Closely related to that is to delete unwanted data, right? When you hit the asteroid, the big one needs to go away. So you need to get rid of the old one, put 2 new ones in. Finally, on this list, we have search for data of some value. We haven't done search too much in our programs that we've been talking about. If you're shooting a missile at something and you want to actually have the missile blow up the asteroid, you need to search through all the asteroids to find out if there's a collision, but that's pretty much the only search that we have done so far. A more kind of standard kind of search idea is you've got some kind of search key, Smith, and you want to, in the phone book data structure that you've got, your query spoken as a sentence is, give me Smith's phone number. And basically what has to happen is the data organization needs to provide support for you doing something with the data in order to find the phone number that is associated with Smith. So those are the actions that you'd like to be able to take. And we've talked about already how arrays do this stuff, you know, in great length, really. And so here's an array up here, and you can think of as an array list as being equivalent where many of these operations are internal to the array list machinery. But I'll show you what the arrays version of this thing is. So to store data, it's very simple. If you have a spot where you want to put your data, let's say you've already used that spot for something and you just want to update its value, array index number 3 equals 33. You know, storing data is very simple. To iterate, you know, this is why we built the for loop, is, you know, that's why it has existed since the 1950s. Go through the array and do something. In this case, what I'm doing is adding up all the values of the array. So sum equals 0 at the start. I didn't show that. Sum equals sum plus r index I. Now I'm presuming that the size of this thing is 10 elements in the array, although I'm only showing 7 up here. To add an element to the list, this is under the presumption that you've got an array that has more space than you actually have values for. You have an indicator that last is the last element in the list. It's the index where there's space. And so you say r.last equals new number, whatever it is. And then you increment last to again point at the spot where there will be space for a new item. Delete, shown up here on the right, there's another iteration. But the way it works is you start j one step beyond the thing you want to delete, because I'm deleting element I, and then you say rj minus I equals rj. And the reason why I'm using j here is because I is indicating the location of the thing I want to delete. And all it does is just takes all the items. You know, let's say I wanted to delete 2, puts 3 down to 2, 4 down to 3, 5 down to 4, 6 down to 5, and we need to update this last thing if we were managing that ourselves. If we were doing it with array list, we would just call, you know, arraylist.remove or something. And finally, searching for 42. If you don't know anything about what's going on in the array, you're stuck with linear search, and that's what this is. That is to say, iterate through all the items until you find something. So this goes from first to last. If the thing I'm searching for is the value 42, if the value is 42, then success. And I'm just using that as a kind of a keyword to indicate I found it, further processing required, but I'm not telling you the details of that in the interest of fitting all this stuff on a single slide. Okay. So we kind of already understand how arrays work, and they're very straightforward and easy to understand. They're also very compact in terms of their storage. You know, every item is right beside the next one in a contiguous chunk of memory. We don't really deal too directly with memory in Java. We just kind of leave that up to the Java system to manage memory for us. But, you know, it efficiently uses space. And for certain types of things like iterating, it's an efficient, computationally efficient to iterate through items that are all in a row. So, however, sometimes it's the case that you want to do something much more frequently than adding and deleting, than iterating through the list. It might be that what you really want to do is just store a bunch of items and then access them occasionally, and also fairly frequently add items to the list and chuck stuff out of the list. And so that's what this linked list thing is about. So a linked list is a special data structure that is a chain of nodes. And so each one of these things up here is a node. So this is a node. So is this one, this one, this one, this one. 0, 1, 2, 3, 4. I'm using sequential numbers for the values in the array. And each node links to the next node. Okay, so there's actually 2 elements in the array. A node has a value, which we're just saying is an integer here, and that's the orange. And it also has a pointer to the next node. And the name of the pointer, or the reference, is next. And interestingly, this is a recursive definition, right? So the class node contains a variable in it that is of type node. That is to say, its type is being used inside the type specification, which is kind of funky. But the reason why you can do this is that, once again, 2 passes through the compiler. The first one gathers all the names, including node and value and next and so on. The next one, the second pass, you know, the one that really counts, is the one that determines the types and the space needed. The reason why this functions is that a reference to a node, which is what this thing is, takes that same amount of space no matter what thing it's pointing at, because you're not actually storing the value, you're storing a reference, and all references are the same size, if you care about that backroom kind of detail. So here's a node. and it's got a value and a next pointer. Here's another node with its value and next pointer. And the way the thing works, just as you can see, you have a special pointer that is of type node that points at the first one. Typically you would call it first, points at the first one, and then each node subsequently points at its next node. There's a special value for the last node in the list, and that is this value is null, and it's a standard kind of method of depicting these visually, and that is to have an arrow pointing to the ground. Often you see the electrical ground symbol there, but that's hard to find in PowerPoint, so I didn't do it that way. So one of the advantages of this thing is that inserting a new item is faster than doing it in an array. And basically, it's about moving pointers around. And I'll show you a picture of that and some code on the subsequent slides. Deleting is also faster than the array, particularly if both inserting and deleting is happening with the first item in the list. And you can compute for yourself what kind of things you would need to do in order to add an item here or remove an item here. And so, adding and deleting, it's fairly straightforward and can be very, very quick if you do it at the head, which is, the starting point of the list, which is what we're going to show you on the subsequent slides. So head insertion is fast, deletion is fast of the first item. The thing that takes a little bit of time and probably would end up taking more time than doing the same thing in an array is searching. So what you do is you follow the first pointer and say first dot item, first dot value, is it equal to the thing I'm looking for? If not, then you have an extra pointer whose job it is that we would call cursor. Go to the next item. And that means just simply assigning this value to the cursor pointer, and that instantaneously points at this. And so it's a similar iteration, but there's a lower level of memory efficiency for doing that for technical reasons that we're not going to deal with. So here are the algorithms for this, and again, these are a little simplified. So first, if you want to store an item in a node that already exists, you just say n.value, where n is of type node and is essentially pointing at one of these things. So n.value is 33. Let's say n equals the first pointer. Then now the value of 33 would end up here. To iterate, here's that pointer following thing I was saying verbally on the previous slide. N equals first. That's that one. And while n doesn't equal null, that is to say it's not a null pointer, that it's not pointing at nothing, and what I'm doing is iterating, and so what I'm going to do is to set sum equal to 0 and then add the value of all of these nodes. So n equals sum plus equals n dot value, and then n equals n dot next. So n is this cursor thing. It's just a little bit more brief way to put it. To add an item, I'm showing it here, and this is adding a node at the beginning of the list. It's once again head insertion. First you construct it, and I'm giving it its initial value here, 12. Then n.next equals first. You have this node point at this thing, right? And it's getting its value from the first pointer. And then first equals n. And then you have the first pointer point at the new node. So essentially 3 operations. First, a construction, and then 2 assignment statements. So it's super fast. To delete, you need to do, again, a little bit more activity in order to make the deletion work. I'll show you a picture of this on the next slide. But again, there's fundamentally, once you've found the thing you need to delete, you then need to, what's the word? You need to, just essentially have the pointer that formerly pointed at the thing you want to delete point at the next thing. And I'll show you a picture because this is a little unclear. To search for 42, this is what I'd said verbally on the previous slide. N equals first while n doesn't equal null. If n dot value equals 42, success, and you do what I found it means. Otherwise, you just simply fall through the loop, and n equals n dot next. And once again, you evaluate whether the n is a null pointer. And so when n is here, if you say n equals n dot next, then n will end up with the value null, and then the loop will exit. And so here's a repeat of what the 2 fields in the node type are. Okay, so now let's show pictures of that. I'm going to show creation insertion first. So here is the same structure we had before. I've moved it down a little. And there is construction of the node, and I've given it the value 7 to start with. And the pointer, for clarity, I've set its initial value to be null, so it's pointing at nothing. So to insert it, we just have its next pointer equal to the same value that first is. So because of the geography of this, the geometry of this thing, these both have the same pointer value. But they look different because of the different origin locations of these arrows. So both this and this thing are pointing at node 0. And the next phase of insertion is to set first pointer to point at this thing. So that's it, 2 assignment statements, very straightforward. Okay, now what I would like to do is show you how to delete. And what I wanted to do is to delete the node that has a 2 in it, and that's this guy here. And so what I'm going to do first is show you searching. So we have the cursor pointer pointing at equal to first, and we have this previous pointer. On the slide previously, it was N1. The purpose of the previous pointer is to point at the item before the item that the cursor is pointing at. So in the loop, I check, is the cursor pointing at the item that I want to delete? I'm looking for 2, so it is not. So what I do next is assign previous equal to first pointer, and then assign cursor to be cursor.next. Bam, and that points at that one now. And I then check, is this one equal to 2? It isn't, so therefore I set previous to be equal to cursor, and then cursor to point at cursor.next, and then I check, is 1 the thing I'm looking for? It isn't, keep going. Now I check, is 2 the thing I'm looking for? It is in fact that one, so now we see why we have these 2 pointers. What I'm going to do now is I'm going to have this node, 1, have its next pointer point at 3, no longer point at 1, and then I'm going to resolve some problems there. So the next stage is I've got the previous pointer and the next pointer set up correctly. Now what I do is I say prev.next equals cursor.next. So assign the value that's here into there. And the outcome of this is that these are both pointing at this node. And then the next thing to do, mainly just to be clear about what's going on, I set this thing to point at nothing. So cursor.next equals null. And typically this will be inside a function. When I exit this function or procedure, when I exit the method, what will happen is that these 2 pointers will disappear, and this thing will be left out there in the middle of nowhere. And what Java's memory management will do is it will discover that nothing's pointing at this and get rid of it. In a programming language like C or C++ and examples that you may see online, you might have to explicitly delete this operation, but you don't have to do that in Java. Java handles all that for you. Okay, so that is kind of a brief example of how a linked list works with insertion and deletion, the simplest forms of insertion, a simple form of insertion and deletion of an item somewhere in the middle of the list. But one of the things I did want to point out is kind of it's not really an aside, but it's an important consideration for us to think about. And unlike some of this, some of the lecture material, which is primarily aimed at folks who don't have programming experience, the thing I wanted to talk about was that in computer science, one of the things that's very important for computer scientists to get really good at is to understand how to build efficient algorithms and to work off a specification that specifies clearly and concisely what is needed, and in that specification develop an efficient piece of code that efficiently uses resources. Because in some ways it's an engineering type of discipline and we care about efficiency in computing. However, this is CIAT, and you might think, okay, so what's your point, dude? What is typically the case in computing is not always the case for the kind of code that might be written by folks pursuing a degree, a graduate degree indeed, in CIAT, because we have other concerns that we care about. So there has been a recent sort of elucidation of, sort of the stages of design work that you can be framed by a very pithy statement, and that is, first, get the result, sorry, I screwed it up. First, get the right design, then get the design right. Now, that reordering of those words means, first, make sure that you're solving the correct problem, that you're solving the problem that really needs to be solved before you work on perfecting how that solution functions. The way it works and manifests here in IAT806 and perhaps throughout your studies, if you're developing programs or when you're developing programs, you often care about the time that computation takes. And it's okay if unimportant things run slow. Important stuff needs to go fast. And what that means, what is important stuff? Well, it's stuff that gets run all the time within your program. Now, within the small programs like the clock and the assignments I've asked you to do, all that stuff is equally important because all the code is very small and compact. But as programs grow, there are certain things that you need to make sure are efficient so that you can deliver true interactivity with very low latency. But there's some other stuff that it's okay if an inefficient algorithm is in play. And so stuff that gets run all the time is stuff that is repeated often in the program and is often the inner loop of a process that is important to the functioning of your program. So the inner loop is this slang term I use, and that kind of inner loop thing, that thing that gets run frequently, you often want to make that efficient, but it is not absolutely a requirement to make everything efficient for all purposes for every time you do this. You know, you need to take some care as to what it is that you optimize. So, what's important? Well, one of the things that, when you're telling a computer scientist or an engineer to make things efficient, you're kind of assuming that the engineer or computer scientist's time isn't important. But in grad school, that's not the case. I mean, you're paying for this. So your time is important. And it is always the case that the runtime of the program doesn't equal the amount of time it takes to create the program. And in particular, if any old algorithm will work and you're only going to do it once or twice, then it's probably sensible to use it. However, if you're going to run it millions of times, or at least lots and lots, 10 times a day for the rest of your dissertation, then it will pay off to make things a little bit more efficient. This is general advice also for folks who are, doing computer science kind of work. Don't prematurely optimize. Donald Knuth, is one of the founders of the field of computer science, said, premature optimization is a cardinal sin. I'm misquoting, but he does make a point that, sometimes if you optimize before you're really ready for it, you might be optimizing something that doesn't matter. Okay, so given that little aside, that important aside about the importance of optimization, now let's talk about another classic data structure that is about enabling efficient activities, particularly search. So a tree is another node link structure, and it is designed for the purposes of enabling fast searching. That's what it's for, okay? Fast searching. So what do we do? So what do we have as operations? Store, iterate, add, delete, search. So writing the code is of storing, a little bit like a linked list, similar kind of code complexity as to what we showed before, and runtime is approximately as fast. A little bit slower, and I'll show you why in a bit. Iterating, it's a little bit more complex to write, it's straightforward, and just about as fast. Not as fast as doing an array, but, reasonable. Adding is a little bit more complex, takes a little bit more time than, say, adding it to a linked list, but compared to adding to an array, somewhere in the middle, with a tree, you don't have to do that copying of stuff to move it out of the way to create space. So it will be a little faster than an array, but a little slower than a linked list. Deleting, more complex, a little slower than a linked list. But finally, search, it's a little bit more complex, not by much, just a little, but much, much faster, like way faster. So let's talk about what a tree is by showing you some pictures. So here is what is known as a binary search tree. This is a particular example. It has people's names in the list. And starting at the top is Gene, and then here's Dennis, Brian, Fred, Kay, Richard, Xenia, blah, blah, blah. So there's something important about this tree, and what I'd like you to do is to think about what that important property is in this tree. Okay, now that you've thought about it, the important thing that is about the tree is this thing up at the top is the root of the tree. And each node, each one of these squares is a node, has 2 pointers, one pointing to the left and one pointing to the right. Down here, I've not shown the pointers. They're pointing at nothing, all of these pointers down here at the bottom. And you could have just a single child to the left or to the right. These are called nodes. These nodes here, which are at the bottom and point at nothing, these are called leaf nodes. The other terminology is that this is the parent of this child and of this child, and this is the root of the tree. So we kind of mix terminology between people and trees here. Root and leaves, parent and child. Okay, the important property that you've no doubt visually understood is that every node to the left, for each node, all the nodes to the left are less than the node in question, and all the nodes to the right, descending from the right, are greater than the node of interest. So everything to the left of Gene, Dennis, Fred, Edward, James, Charles, Andrew, Brian, all of those values are less than Gene. And all the values to the right of Gene, Richard, Kay, Joyce, Peter, Steve, Yvonne, Xenia, those are all greater than. So what that means is if you're doing a search, you can start here. Let's say I'm searching for Xenia. Well, Xenia is greater than Gene, so I know I can safely go over here to the right to do further searching, and I've eliminated half plus 1 of the entire search space that I need to look at. So I'm looking for Xenia, it's greater than Richard, go to the right. I'm looking for Xenia, I found it, bam. So 3 search queries essentially, and link following 3 times, follow the first link to get to the root. That's a very, very quick mode of searching. And basically the number of those little search queries that you need to do is equal to the depth of the tree, the number of layers. So this is layer 1, 2, 3, 4. So the most searches you would need to do in this tree is 4. Think about that, about how the size of this tree grows, but the number of levels increases somewhat more slowly than the number of nodes that are present in the tree. Okay, so let me talk about the definition now. I'm changing my representation to this kind of purple and orange thing. And so once again, a binary search tree is a node, and this time binary search tree nodes have 2 links, the left child and the right child. The top node is the root, as I said, and nodes at the bottom without children, such nodes are called a leaf. It's called a binary search tree because it has 2 children. Okay, there are other kind of tree shapes which have more children. B tree is an example of that. It's called a search tree because of the way in which the nodes are arranged. The property of all this stuff to the left is less than, and all the stuff to the right is greater than, or perhaps greater than equal to. But in any case, that relationship is true throughout the tree. Every node has lesser values to the left and greater values to the right. So here is our binary search tree again with the more details shown. We have the root pointer, we have this node 3 that has a left pointer to 1, a right pointer to 5, blah, blah, blah. And here are all the leaf nodes, and each of those leaf nodes has 2 null pointers associated with it. So you can see there's a little bit of overhead in this thing. It's an integer and 2 pointers. Typically, though, you want to have a payload, so to speak, that has more than just the key, that there's other stuff that's being stored in a binary tree, so that it's not the case that the pointers are really occupying way more memory than everything else. Okay, so what I'd like to do now is just say in text what I'd already said in terms of its property. For any node n, to the left, all child values are less than n, and to the right, all child values are greater than n. And as you probably have guessed already, this is another one of these recursive definitions. And the notion of recursion is kind of pop up again and again throughout our discussion. In particular, you'll see an algorithm that's recursive later on, because the structure of treeness is repeated for every node throughout the thing. So you can run, say, search or traversal on a node, have it be a recursive algorithm, and you can apply that to every single one of the subnodes in the tree. And the recursive definition goes hand in hand with the recursive algorithm. Okay, so once again, there's the tree. So typically, however, given that tree, each node has 3 or 4 parts. It certainly needs the first part, which is the key, typically. And that's the names in the previous picture, Jean, Yvonne, etc., and in the numbers in the colorful tree I've been showing. The other thing that's not shown in these, well, Jean is kind of an example of payload, but is the other stuff associated, say, with Jean or with Xenia or with Yvonne, which is, the name and address or something like that, the phone number. The other thing that is necessary is a left child pointer and a right child pointer. And of course, the types of both of those things are, binary node. And so here's an example of binary search tree search. So here's our node type, just showing the fields only. We have int key, so we're just searching for integers again, and 2 B nodes, left and right. So once again, the definition of this class has the use of this class right here in its field. And there's 2 nodes that we need. One is B node type things outside of the individual tree. One is the root, where the tree we're interested in lives. If you want to find the tree, you've got to go to the root, and you need a pointer for that. And this other thing, cursor, whose job it is, cursor indicate from Latin cursus, to run. Its job is to run through the tree and do things for you. So to search, you set cursor equal to root so that it's pointing the same thing. And while cursor doesn't equals null, that is, it's not a null pointer. If the thing you're searching for equals the cursor key, then success. And success, once again, says, I found it, do something with it. If otherwise, and presumably you return out of a function that's doing this. Otherwise, if search is greater than cursor.key, cursor equals cursor.right, follow the right pointer. Otherwise, follow the left pointer. So it's either equal, greater than, or less than. And this is the equal case, this is the greater than case, and therefore everything else is the less than case. So you go to the left there. Okay, so what I'm going to do now is show binary search. I'm going to search for the item 6. So we start off with a cursor pointer pointing at, say, nothing. You set binary, the cursor equal to root, so now it's pointing at 3. And I'm searching for 6. So is 6 equal to 3? No. Is it greater than 3? Yes, it is. Cursor equal cursor.right. Bam. It's now pointing at 5. Is 5 equal to 6? Nope. Is it greater than 6? Yep. Cursor equals cursor.right. And there it is. We've found the item. Is 6 equal to 6? Yes, we found it. And presumably you do something with the information that is also stored in 6, the payload, as it were. Okay, so that's just a quick illustration of how binary search works. I did a little bit of algorithm animation here to kind of show what it's like. And each time the green arrow jumps from one thing to the next, it's just a single assignment statement. So that's really basic and fundamental computer stuff. It takes place in 2 instructions or something like that. Very, very simple. So let me go back. To insert a value, the first thing you need to do is to find the spot where it would go. And then the next thing you would need to do is to adjust one of the pointers in the tree to point at a new item. So I'm not going to illustrate this with another algorithm animation, but I am going to say, let's pretend that these are now floats, and that the values that we're interested in, the value I want to add is 2.5. So what I do is I say, create a new node, that stick 2.5 in it, and then I do an insertion operation. The first thing I do is search for 2.5. Is 2.5 less than 3? Yes, it is. Is 2.5 less than, equal to, or greater than 1? Greater than 1. Is it greater than 2? Yes, greater than 2. I now have a null pointer here. And so therefore what I do is I set the right pointer of this node to point at the new node. The new node has both of them null pointers. Now, if I were to continue to insert things randomly throughout this tree, I could cross my fingers and hope that the tree maintains this kind of nice shape that I've got going on down here. But typically in real binary trees, built by folks who are really trying to make binary trees work well, there is a balancing operation that needs to take place to make sure you don't get funky shapes. And that's what's going on. That's an example of a funky shape here. I've got an unbalanced tree, Unbalanced has a formal definition, that is to say the minimum and maximum depth can be no greater than 1, a difference between those two. But the minimum depth here is, 2 versus 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. There's a difference in depth, and so this isn't a great tree for searching. This is also indicating delete, and what you have to do something fairly similar. You have to have something that is going to be the recipient of, what the stuff that I'm going to disappear at node 9, and so I need I need node 5 to point at node 7 once I've deleted node 9. And it can be complicated. The other thing that would need to happen is also the balancing operation might need to take place, because the shape of the tree might, be not so good for searching. So iterate, going through, it looks like, oh my God, how do you iterate this thing with pointers going everywhere? And it turns out it's very simple. And this is, once again, the recursive algorithm that I was alluding to earlier. And this is called in-order traversal. There's 2 other traversal types, but this one makes the most sense. And the way it works is, you call in order on, say, root. And if that pointer is null, you return. Okay? Otherwise, you call in order on the left node, right? A recursive call to in order. You print, let's say the purpose of in order is to print the contents. You print out the item that you're in, cursor.key, and then you call in order on cursor.right. So in order on cursor left, do the thing on cursor.self key, and then in order on cursor.right. So let's go 2 slides back. Call in order on this. First, given that we got this one, okay, call in order, it's not null, so we're good. Call in order on the one on the left. Call in order on this one's left. Call in order on this one's left, that's null, so that returns right away. Now print cursor.key, so print 0. Call in order on cursor right, that's null, return. So I'm not going to say null anymore, all right? We'll return, that returns in order on left, print 1, in order on right, print 2, return from in order on right, return from in order on right, print 3, and so on and so forth. So I recognize that, I've said in order a lot. You might want to, print this out or something like that and follow along the in order thing in order to assure you that, yes, this thing works. One of the things that I found when I was learning this stuff for the first time and going, I just had this kind of breakdown of trust. How can this work? Because so much of how this thing functions is implicit, right? But it does work. And the reason why it works is because you have to enforce the property that everything to the left is less than and everything to the right of a node is greater than, descending from that individual node. That recursive property assures that the recursive activities, the recursive processes that you do, follow that property, and in this case, print out the elements in order, which is why this is called in order. Okay, so this is the last slide for trees and linked lists. Things are not necessarily perfect, and I've talked about this a little bit already. What that means is that unbalanced trees can sometimes happen if you don't have some kind of process to fix them up. Real trees built by, say, Java's the software development kit do this balancing behind the scenes for you to make sure that the trees are balanced that you have. And the reason why this can get balanced is, think of adding elements to the tree without doing a rebalancing. So you start off adding node 1, then add node 3. Where does it go? It goes to the right of 1. Where else? And then add node 5. Well, it goes to the right of 1, to the right of 3. Where does 6 go? It goes to the right of 1, right of 3, right of 5, etc., etc. So if you were to add items in order without balancing, you'd end up with a shape like this. And so what has to happen is that the algorithms that manage an algorithm that manages this tree needs to balance that tree, either, every now and then, or every time you do an addition or a deletion. But I'm not going to get into the details of that because, that's not my purpose of focus. So that wraps up the conversation that we are going to have about linked lists and binary trees, and that's the end of the lecture for IAT806.